Welcome. In this lecture, we're going to go through a second method for writing sets, and this is one of the ones that you perhaps will see more commonly used, and it's also it takes a little longer to get used to, I think. So this is method 2, and in this one, you're going to define sets using a rule. So define sets using a rule. So I'll show you how to do this. Okay. So when I write, I'm gonna have kind of a consistent little bit of a color scheme here. So let's just get these markers. So I'm gonna say that when I write like this, so this is gonna be the set of all things like A. So the set of all elements of the form A satisfying B. Okay, so this is so this part here is the set of all, and then from here we get elements of the form A satisfying, so you can think of the middle as satisfying the condition B. So condition B, whatever that is. Okay. So let's look at some examples. It's always helpful to look at examples. So here we go. Examples. So the first one would be if I were to write the set of all A satisfying A is a positive integer. Okay, so when I write something like that, I usually just mean this is just the set. So 1, 2, 3, 4, and so on. So I could have listed this one. I could also use this notation, for the natural numbers, although this can get a little bit confusing because in some countries this includes 0 and in some countries it doesn't. Here's another, so this is the set of all. So the set of all A satisfying that A is a positive integer, just to kind of decode. Okay, so that's precisely kind of how to decode like that. And then let's just try one more. So we would have, so the next one would be the set of all. So the set of all real numbers A satisfying that A squared equals 2. So this could actually just be, so this is actually just a set, which is the minus square root of 2 and the square root of 2, And so it's okay that this is finite. So okay that finite, we can still use that notation. The notation works for finite sets too, if you can write them like this. The notation can work for finite sets too. So the notation can work for finite sets too. Okay. And so this one, let's go ahead and write this again, kind of interpreting like this. So this is the set of all. And then we have real numbers A satisfying that And then we have a squared equals 2. Okay, and there's kind of like a little bit of our caution with this particular example. So here's kind of our cautionary tale. Maybe I'll write it like this. So note okay, that our requirement that A is an R, so actually I'm going to write this down here. So note our requirement, right, that we have here, that A is an R, can have an impact on the set. That A is an R, like the real numbers, can have an impact on the set. Right? So let's think of, so for example, if I wrote the set of all, so if instead I wrote the set of all A and R, right, such that A squared equals 2. Oh, this set of all A, this was what I had before, but if I added to this and put, oops, as long as I'm erasing there, I'll erase this. I will use up here, I just decided to put this down here. So R, the set of all R greater than or equal to 0, satisfying that A squared equals 2, right? I would get a different set here. I would get this set, this would just be the set that's the square root of 2. I would leave out the square root of -2, okay? And I could get this even worse. So if I required that the A was actually an integer, okay, then, right, but I mean, with exactly the same requirements here, that I would actually get the empty set. There would be nothing in there, right? Because neither the square root of 2 nor minus the square root of 2 is an integer. So this is kind of a lesson in the importance of what's here and how that can really restrict what the elements are. Let's do one last example here. So we're going to do 3, which is going to be, so now we have the set of all B squared. So let's do the set of all, and we have B squared, such that B is an integer. Right? So what does this end up looking like? So this ends up looking like 0, 1, 4, 9, and so on. Right? You're just taking the squares of all the integers. Okay? And so this one is can be written as the set of all, right, B squared, satisfying that and then we have B as an integer. And this is actually okay, this kind of flopping around. So sometimes the restricting conditions are actually on the left. And so, you know, you're saying elements of the form B squared. Like there's nothing wrong with that. And then it's still satisfying that B is an integer. So while a lot of times we kind of set our notation or like our universe of discourse, as we might say, on this side, then sometimes it's actually not true. Sometimes there's like a formula or something on the left-hand side, and that's totally okay. Okay, so I know this notation can take a little bit to get used to, but it's very useful, compact notation, and once you get used to it, it's not all that bad, and people use it a lot. So it's worth getting used to, even though, of course, notation always feels overwhelming in the beginning. Okay, so I hope that made some sense. It was helpful, and I will see you in the next lecture.